Before the first stars ever formed, before planets existed, and long before life appeared, the universe was already becoming cold. Today the sun pours enormous amounts of energy into space every second, yet the vast emptiness between the stars remains unimaginably cold. How can a universe filled with blazing stars still be dominated by darkness and freezing temperatures? In this relaxing journey through the hidden physics of space, discover why the cosmos stays so cold despite the sun's incredible heat, and what this surprising mystery reveals about the nature of the universe itself. If you enjoy calm science documentaries for sleep relaxation and learning, please like this video, subscribe to Cosmic Bedtime Stories, and join us as we drift into one of the most fascinating mysteries in all of space. Far beyond the familiar outlines of planets, stars, and galaxies, the universe extends into regions so large that ordinary distances lose much of their meaning. Space on its greatest scales is not filled with bright objects. It is dominated by separation. Galaxies gather in enormous groups and filaments, yet between these structures lie expanses so vast that even light requires millions of years to cross them. In these remote regions, the universe presents one of its most surprising characteristics. Despite containing countless stars and enormous amounts of energy, it remains overwhelmingly cold. The largest environment known to astronomy is not a galaxy or a cluster of galaxies, it is the universe itself. Observations indicate that the observable universe stretches for tens of billions of light-years in every direction. Within this immense volume are hundreds of billions of galaxies, each containing billions or even trillions of stars. Seen from a distance, such abundance may suggest a cosmos overflowing with warmth and brightness. Yet the reality is different. Most of the universe is dark space lying far from any significant source of heat. Temperature in its simplest sense describes the average energy of particles. Hotter environments contain particles moving with greater energy. Colder environments contain particles with less energy. On Earth, temperature is often associated with weather, sunlight, water, and air. In the wider cosmos, temperature becomes linked to the distribution of energy across enormous distances. Because the universe is mostly empty, energy is spread thinly through vast volumes of space. When astronomers discuss the average temperature of the universe, they often refer to a faint glow that fills all of space. This glow is known as the cosmic microwave background. It is not produced by modern stars or galaxies. Instead, it is ancient light originating from the early universe. Observations show that this radiation fills space in nearly every direction, with remarkable uniformity. Today it corresponds to a temperature only a few degrees above absolute zero, the theoretical limit at which particles possess the least possible thermal motion allowed by physics. This ancient radiation provides an important clue about the thermal character of the cosmos. Even in regions completely removed from stars, planets, and galaxies, space is not entirely empty of energy. The cosmic microwave background forms a faint thermal bath that surrounds everything. Yet it is extraordinarily cold. Any object drifting alone through the depths of intergalactic space would gradually exchange energy with this surrounding radiation and tend toward a similarly low temperature. The presence of this background glow reflects the history of the universe itself. Scientific observations indicate that the universe began in a much hotter and denser state than it possesses today. In its early stages, matter and radiation existed together in conditions of immense energy. As the universe expanded over billions of years, the radiation stretched along with space. Its energy decreased, its temperature fell. What remains today is a cooled remnant of that earlier era spread across the entire observable cosmos. From the perspective of daily experience, such coldness may seem difficult to reconcile with the existence of countless stars. Every star releases tremendous amounts of energy. The sun alone emits more energy each second than human civilization could use across many millions of years. Across the observable universe, stars collectively generate extraordinary quantities of light and heat, yet their influence is limited by distance. The space between them is so enormous that most locations remain far removed from any substantial source of warming. A useful comparison comes from considering a small campfire in a vast desert at night. Close to the fire, warmth is easily felt. A short distance away, the effect becomes weaker. Far enough from the flames, the surrounding darkness dominates. In the cosmos, the contrast is even greater because the distances are incomparably larger. Stars occupy only tiny portions of the total volume of the universe. Their heat does not fill all of space equally. Instead, warmth tends to remain concentrated near the stars themselves. Viewed on the larger scales, galaxies resemble scattered islands surrounded by immense oceans of darkness. The light emitted by stars travels enormous distances, but the volume through which that energy spreads increases continuously. As a result, the energy available in any particular region becomes progressively smaller with distance from its source. The farther one moves from concentrations of stars, the colder the surrounding environment generally becomes. Astronomers have measured temperatures in many different cosmic settings. The surfaces of stars can reach thousands or even tens of thousands of degrees. Certain regions around stellar explosions become far hotter. By contrast, the average background temperature of the universe remains only a few degrees above absolute zero. This difference illustrates how unevenly energy is distributed across cosmic scales. Hot regions certainly exist, but they occupy only a tiny fraction of the total volume. The coldness of the universe is therefore not a contradiction. It is a consequence of scale. The observable cosmos is unimaginably large. Even though it contains immense energy, that energy is dispersed across distances beyond ordinary comprehension. Most regions are located far from stars, far from planets, and far from concentrated sources of radiation. The dominant condition becomes not intense heat but extreme sparsity. Modern observations from space telescopes and ground-based observatories reveal a cosmos structured by this balance between localized brightness and widespread darkness. Galaxies shine, stars shine, nebulae shine, yet the overwhelming majority of the cosmic volume remains occupied by regions where matter is scarce and temperatures remain very low. The universe contains brilliant sources of energy, but they exist like scattered lanterns within an environment whose defining characteristic is vast emptiness. Across the largest observable scales, coldness is not an unusual feature of the cosmos. It is the normal state. The ancient glow of the cosmic microwave background provides a faint thermal foundation, while isolated concentrations of matter create pockets of warmth. Between those pockets stretches an immense realm, where little matter exists and where energy is spread thinly across unimaginable distances. In this grand setting, the average temperature of the universe reflects not the power of its stars but the enormity of the space that separates them. Beyond the great collections of galaxies lies another layer of cosmic structure that becomes visible only when astronomers map the universe on its largest scales. Galaxies do not occupy space evenly. Instead, they gather into clusters, groups, and immense filaments that stretch across hundreds of millions of light years. Between these structures lie enormous regions known as cosmic voids. These voids represent some of the emptiest environments known in nature, and they provide an important setting for understanding why the universe remains so cold. A cosmic void is not completely empty. Even the most isolated regions contain traces of matter, scattered particles, and the faint glow of radiation that fills the cosmos. Yet compared with the crowded environments of galaxies and clusters, these regions are remarkably sparse. Observations indicate that some voids span tens of millions of light years, while the largest extend across hundreds of millions of light years. Within such vast volumes, galaxies become rare. In some places, an observer could travel enormous distances without encountering a major concentration of stars. The discovery of these voids emerged gradually as astronomical surveys expanded. Early maps of galaxies suggested that matter might be distributed somewhat uniformly across space. As observations improved, a more complex picture appeared. Galaxies were found to arrange themselves into gigantic networks often described as the cosmic web. Dense filaments connect clusters and superclusters, while immense gaps separate them. These gaps are the voids. From a thermal perspective, voids offer a clear demonstration of how distance influences temperature. Heat sources in the universe are generally associated with matter. Stars emit radiation. Galaxies contain billions of stars. Clusters of galaxies contain hot gas and energetic phenomena. In cosmic voids, such sources become scarce. The absence of concentrated matter means the absence of concentrated heating. Imagine standing in a city illuminated by countless lights. Even at night, energy surrounds every street and building. Now imagine moving farther and farther into an uninhabited wilderness. The number of nearby light sources steadily decreases. Eventually, only a few distant glows remain on the horizon. Cosmic voids resemble this transition on a scale so immense that ordinary comparisons become inadequate. The nearest significant galaxy may lie millions of light years away. The radiation emitted by distant galaxies still passes through these regions. Light does not stop at the boundaries of a void. Photons continue traveling across space, crossing immense distances. Yet because the sources are so remote, the amount of energy present within any particular volume remains extremely small. The energy arriving from countless distant objects becomes diluted across enormous expanses. Within a cosmic void, the dominant thermal influence is often the cosmic microwave background. This ancient radiation fills all directions with extraordinary uniformity. Because nearby sources contribute relatively little additional energy, objects drifting through the deepest voids gradually approach temperatures governed largely by this background radiation. In this sense, voids reveal the baseline thermal condition of the modern universe. Matter itself behaves differently in such environments. In galaxies, particles frequently interact with surrounding gas-dust magnetic fields and radiation. In voids, encounters become far less common. The density of matter may be many times lower than the cosmic average. Individual particles can travel immense distances before interacting significantly with other particles. This scarcity contributes to the persistence of cold conditions. Astronomers study cosmic voids not only because of their emptiness, but also because they provide clues about the evolution of the universe. Observations indicate that these regions grow over time. As gravity pulls matter toward denser structures, voids become emptier. Galaxies migrate toward filaments and clusters, leaving behind regions with increasingly little matter. The result is a gradual strengthening of the contrast between crowded and sparse environments. This process influences temperature distribution as well. Dense regions accumulate matter capable of producing radiation and heating surrounding gas. Sparse regions lose much of that potential. Over billions of years, the largest voids become environments where energy sources are especially distant and diffuse. Their thermal character remains dominated by coldness. Despite their emptiness, voids are not completely featureless. Astronomers detect traces of gas flowing through them. Some isolated galaxies exist within their boundaries. Dark matter, which exerts gravitational influence yet does not emit light in the ordinary sense, is also present. Nevertheless, the overall density remains extremely low compared with more populated regions of the cosmic web. The scale of these voids is difficult to comprehend. Light itself travelling at the fastest speed known in nature requires millions of years to cross many of them. Human history occupies only a tiny fraction of such durations. Entire civilizations could rise and disappear while a beam of light advances through a portion of one large void. These immense dimensions reinforce a central reality of the cosmos. Space is not merely large, it is overwhelmingly dominated by separation. Temperature reflects this separation. Heat does not accumulate efficiently when matter is scarce, and sources of radiation are distant. Even though energetic galaxies surround a void from afar, their influence weakens across the enormous distances involved. The resulting environment remains cold not because energy is absent everywhere, but because energy is distributed across volumes of staggering size. Modern cosmology views cosmic voids as essential components of the large-scale structure of the universe. They occupy a substantial fraction of cosmic volume. While galaxies attract attention through their brightness, voids reveal the character of the spaces between them. They demonstrate that the universe is not primarily a collection of luminous objects. It is primarily a vast framework of mostly empty regions punctuated by islands of matter and light. Within these immense cavities, the ancient radiation left from the early universe continues to drift through space. Sparse particles move through regions where encounters are rare. Distant galaxies shine across unimaginable separations. Yet despite the presence of all this energy, the overall environment remains profoundly cold. The reason is found not in a lack of stars but in the extraordinary scale of the emptiness that surrounds them. Between the great structures of the universe lies a realm that appears empty at first glance, but is in reality filled with a thin and subtle presence of matter. This region is known as intergalactic space. It occupies the enormous distances separating galaxies from one another, and serves as the environment through which light travels on its long journeys across the cosmos. Although intergalactic space contains gas radiation and invisible gravitational structures, it remains one of the coldest settings in the known universe. For much of human history, the space between galaxies was imagined as a perfect void. As astronomy advanced, observations revealed a more complicated picture. Sensitive instruments detected traces of matter distributed throughout these immense regions. The density is extraordinarily low compared with anything experienced on Earth. Even the most rarefied laboratory vacuum contains vastly more particles than many portions of intergalactic space. Yet the presence of even a few particles becomes important when considered across distances measured in millions of light years. Most of the ordinary matter found between galaxies exists as hydrogen. Hydrogen is the simplest chemical element consisting of a single proton accompanied by an electron. It formed in great quantities during the early history of the universe and remains the most abundant element in existence. In intergalactic space, hydrogen often appears as an extremely diffuse gas spread across enormous volumes. Helium is also present along with tiny traces of heavier elements produced by generations of stars. The particles occupying these regions do not gather into dense clouds like those found within galaxies. Instead, they are dispersed thinly throughout the cosmic web. In some locations, only a few particles may occupy a volume larger than an ordinary room. In others, the density becomes even lower. This scarcity plays a central role in determining how temperature behaves. Temperature depends not only on how much energy exists, but also on how concentrated that energy remains. A small amount of energy confined to a tiny region can produce high temperatures. The same amount distributed across a vast volume may correspond to very low temperatures. Intergalactic space illustrates this principle on the larger scales. Even though radiation from countless stars passes through it, the energy is spread so thinly that the average thermal environment remains cold. Astronomers observe intergalactic matter through several methods. One of the most important involves studying the light from distant quasars. A quasar is an extremely bright source powered by matter, falling toward a supermassive black hole at the center of a galaxy. As quasar light travels across billions of light years, it passes through clouds of intergalactic gas. Certain wavelengths are absorbed along the way, leaving characteristic patterns in the light. By examining these patterns, astronomers learn about the composition, density, and temperature of matter between galaxies. These observations reveal that intergalactic space is not uniform. Some regions contain slightly denser concentrations of gas associated with the cosmic web. Other areas remain more rarefied. Temperatures vary accordingly. Certain intergalactic gases are warmed by radiation from galaxies and quasars. Others remain closer to the low temperatures established by the background conditions of the universe. One important source of heating comes from ultraviolet radiation, emitted by stars and active galaxies. This energetic light can remove electrons from atoms, a process known as ionization. When ionization occurs, energy is transferred into the gas, raising its temperature. Large portions of intergalactic hydrogen exist in this ionized state. Observations indicate that some intergalactic gas reaches temperatures of thousands or even tens of thousands of degrees. At first glance, these values may seem inconsistent with the idea of a cold universe. Yet temperature and heat content are not identical concepts. A sparse gas can possess a relatively high temperature while containing very little total energy. The particles may move rapidly, but there are so few of them that the overall amount of thermal energy remains small. This distinction becomes especially important in the low-density environments of intergalactic space. An everyday comparison helps clarify the difference. A glowing spark from a fire may possess a very high temperature, yet it contains too little energy to warm an entire room. Similarly, intergalactic gas may exhibit temperatures that sound impressive, while remaining incapable of significantly heating objects located within it. The extreme sparsity of matter limits the practical impact of that thermal energy. Radiation also travels freely through these regions. Unlike heat transfer through direct contact, which requires particles to collide, radiation can cross vast distances through empty space. Light from stars, galaxies, and quasars streams through intergalactic space continuously. However, the farther it travels, the more widely it spreads. As the radiation disperses, the amount of energy present within any given area decreases. The expansion of the universe adds another subtle influence. As space itself expands, the wavelength of traveling radiation stretch. Longer wavelengths correspond to lower energy. Over billions of years, this process reduces the energy carried by ancient light moving through the cosmos. The cosmic microwave background represents the most familiar example of this effect, but the principle applies broadly to radiation traveling across immense distances. Intergalactic space therefore exists in a delicate balance. Sparse matter absorbs energy from distant sources while simultaneously losing energy through radiation and cosmic expansion. No dense atmosphere traps heat. No ocean stores thermal energy. No solid surface gathers warmth from sunlight. Instead, particles drift through an environment where matter is scarce and energy remains widely dispersed. Modern observations show that this diffuse medium plays an important role in cosmic evolution. It serves as a reservoir of material from which galaxies grow. Gas flows along the filaments of the cosmic web, gradually feeding regions where gravity gathers matter into denser structures. Yet despite its importance, the intergalactic medium remains defined by emptiness. The spaces separating galaxies are so enormous that even the presence of vast amounts of gas becomes almost imperceptible when averaged across the total volume. In this setting, the cold nature of the universe becomes easier to understand. The cosmos contains matter and energy between its galaxies, but both are distributed across distances beyond ordinary imagination. Radiation travels through these immense regions and sparse particles absorb portions of that energy. Even so, the overall environment remains dominated by low densities and widely dispersed heat. Intergalactic space reveals that coldness in the universe is not the absence of energy. It is the consequence of energy being stretched across an immense and largely empty cosmic landscape. Around every large galaxy lies a region that extends far beyond the bright spiral arms, glowing star fields and visible clouds often captured in astronomical images. These outer regions are known as galactic halos. They form vast envelopes surrounding galaxies and occupy volumes many times larger than the luminous portions visible through ordinary telescopes. Although halos contain matter, their appearance remains faint because the material is spread across enormous distances. Within these remote outskirts, another aspect of cosmic temperature emerges. Heat and cold coexist in ways that seem unusual when compared with everyday experience. A galaxy such as the Milky Way is often imagined as a bright disk filled with stars. That visible disk is only part of the structure. Beyond it lies a much larger region populated by sparse gas, scattered stars, globular clusters, and vast amounts of dark matter. Dark matter does not emit ordinary light, and cannot be observed directly through conventional telescopes, yet its gravitational influence shapes the structure and motion of galaxies. Together, these components create an extensive halo surrounding the brighter central regions. The halo extends far beyond the regions where most stars reside. If the visible galaxy were compared to a small illuminated town, the halo would resemble an enormous countryside stretching outward in every direction. Distances within these regions are measured in tens or even hundreds of thousands of light years. The farther one moves from the galactic center, the fewer stars appear. Light becomes more scattered, matter becomes increasingly diffuse. Astronomers have discovered that galactic halos contain substantial amounts of gas. Unlike the cool, dense clouds found within some regions of galaxies, much of this halo gas exists in a highly rarefied state. Observations using space-based observatories reveal that portions of the gas reach temperatures of millions of degrees. Such values may seem surprising within a discussion of cosmic coldness. Yet once again, the distinction between temperature and total heat becomes essential. In dense environments, millions of degrees would represent extraordinary amounts of thermal energy. Within a galactic halo, however, particles are separated by enormous distances. The gas is so thin that individual atoms may travel considerable distances before encountering another particle. The measured temperature reflects the energy of those particles, but the total amount of matter present within any small volume remains extremely low. An object placed within such gas would not necessarily experience intense heating. The sparse particles transfer energy inefficiently because collisions occur infrequently. This situation differs greatly from standing within a hot atmosphere on Earth, where countless molecules constantly exchange energy through direct contact. In a galactic halo, the gas may possess a high temperature, while remaining incapable of delivering large amounts of heat to nearby objects. The source of this energetic gas is linked to the life of galaxies themselves. Stars release radiation and stellar winds throughout their existence. Massive stars eventually end their lives in supernova explosions, ejecting material at tremendous speeds. Active regions surrounding supermassive black holes can also accelerate matter and release vast amounts of energy. Over billions of years, these processes inject energy into surrounding gas, helping maintain the hot conditions observed in many galactic halos. At the same time, large portions of the halo remain cold in a broader sense. The volume is immense, the density is low, and energy sources become increasingly distant, with greater separation from the galactic center. Radiation emitted by stars spreads outward through expanding spheres of space. As distance increases, the amount of energy available within any given area decreases substantially. Even though the galaxy may contain hundreds of billions of stars, their collective influence weakens across the vast dimensions of the halo. The outer halo also serves as a boundary region between the galaxy and the wider intergalactic environment. Gas can flow inward from surrounding space, gradually supplying material for future star formation. Other gas can be driven outward by energetic events occurring within the galaxy. Observations indicate that this exchange continues over long, cosmic timescales, linking galaxies to the broader structures of the universe. Within these outskirts, darkness becomes increasingly dominant. The bright concentrations of stars visible from the galactic disk occupy only a small fraction of the total volume. A traveler moving through the outer halo would encounter enormous regions where nearby stars are rare, and where the surrounding environment appears largely empty. Despite the presence of hot gas and invisible dark matter, the overall impression would be one of isolation and vastness. Modern astronomical instruments detect halo gas through several methods. Certain atoms emit or absorb characteristic wavelengths of light. By studying these signatures, astronomers estimate temperature, density, and composition. Observations show that heavier elements such as oxygen, carbon, and silicon exist within halo gas, evidence that material forged inside stars has been transported far beyond the visible portions of galaxies. These elements drift through regions where matter is spread across extraordinary distances. The thermal structure of galactic halos demonstrates that cosmic temperature cannot be understood through a single measurement alone. A region may contain particles moving with considerable energy, while still remaining effectively cold when considered in terms of total heat content and practical heating ability. This distinction becomes increasingly important in space, where densities often fall to levels far below anything encountered on Earth. The halo also reveals how local warmth fades into the larger coldness of the universe. Near the dense stellar populations of a galaxy, radiation is abundant. Energy sources are numerous. As one moves outward, those sources become more distant. Their influence weakens. The sparse gas of the halo continues to carry traces of energetic processes occurring within the galaxy, yet the immense volume ensures that energy remains widely distributed. Across hundreds of thousands of light-years, the halo forms a gradual transition between the concentrated activity of a galaxy and the vast emptiness beyond. It contains hot particles, faint radiation, scattered stars, and enormous regions of darkness. The result is an environment where high measured temperatures can coexist with profound isolation and low overall heat density. In these outskirts, the universe continues to reveal that coldness is not simply the absence of energy. It is often the consequence of energy being dispersed across distances so great that its warming influence becomes remarkably weak. Between the stars of a galaxy lies a vast environment known as the interstellar medium. It fills the spaces separating stellar systems and occupies a significant portion of the visible structure of a galaxy. Although stars dominate astronomical photographs with their brightness, the regions between them contain gas dust, magnetic fields, and radiation that play an essential role in the life cycle of matter. Within these spaces, the relationship between heat and cold becomes especially clear, revealing why most of a galaxy remains far cooler than its stars. The interstellar medium is composed primarily of hydrogen, accompanied by helium and smaller amounts of heavier elements. These heavier elements originate within stars and are released into space through stellar winds and explosive stellar deaths. Over billions of years, generations of stars enrich the interstellar environment with carbon, oxygen, silicon, iron, and many other elements. Despite this ongoing contribution, the overall density of the interstellar medium remains extremely low. Even within regions considered relatively dense by astronomical standards, the number of particles is tiny compared with Earth's atmosphere. A single cubic centimetre of air at sea level contains an enormous number of molecules. In contrast, many regions of interstellar space contain only a few atoms within the same volume. Some areas contain even fewer. Matter exists, but it is spread thinly across immense distances. The sparse nature of this environment strongly influences temperature. Energy arriving from nearby stars is distributed among relatively few particles. At the same time, the low density limits how efficiently heat can be transferred through direct contact. Unlike a warm room on Earth where countless molecules constantly collide and exchange energy, the interstellar medium operates under conditions where collisions occur much less frequently. Astronomers divide the interstellar medium into several broad categories based on density and temperature. Some regions contain relatively warm gas exposed to stellar radiation. Other regions contain hotter ionized gas created by energetic events, such as supernova explosions. Still others remain remarkably cold. These colder regions often attract particular attention because they demonstrate how efficiently matter in space can lose energy. One of the most important processes governing interstellar temperature is radiation. Gas and dust absorb energy from nearby stars and later release some of that energy back into space. Because the surrounding environment is so open, energy can often escape efficiently. Without dense atmospheres or thick layers of material to trap heat, many regions gradually cool over time. Dust grains play a significant role in this process. These tiny solid particles consist of materials such as carbon compounds, silicates, and frozen substances. Although individually microscopic, they are present throughout much of the interstellar medium. Dust absorbs visible and ultraviolet light from stars and re-radiates energy at longer wavelengths. Through this continuous exchange, dust helps regulate the thermal conditions of interstellar space. The influence of stars varies dramatically with distance. Close to a star, radiation is intense. Farther away, its effect weakens rapidly. Since stars occupy only a small fraction of the total volume of a galaxy, much of the interstellar medium exists far from strong heating sources. Light continues to travel through these regions, but the energy available within any given area decreases as distance from the source increases. The average separation between stars is itself enormous. In the region surrounding the solar system, the nearest star beyond the Sun lies more than 4 light-years away. This distance is difficult to imagine on human scales. If the Sun were reduced to the size of a small object held in one hand, the nearest neighbouring star would still be located many hundreds of kilometres away. Such immense separations mean that large volumes of space receive only modest amounts of stellar energy. Observations show that temperatures within the interstellar medium can vary widely. Some hot regions reach thousands or even millions of degrees, yet many other regions remain much colder. Certain diffuse clouds exist only a few tens of degrees above absolute zero. The diversity reflects differences in density, radiation exposure, chemical composition, and local energetic activity. An important feature of interstellar space is its transparency. In many directions, radiation can travel long distances without being absorbed. This transparency allows energy to escape. On Earth, atmospheric gases help retain some of the heat received from the Sun. Oceans store thermal energy and release it gradually. In the interstellar medium, there are no comparable reservoirs capable of maintaining widespread warmth across enormous distances. The balance between heating and cooling remains dynamic. Stars continuously inject energy into their surroundings. Ultraviolet radiation ionizes atoms. Stellar winds push matter outward. Supernova explosions create expanding shock waves that heat nearby gas. Yet these energetic influences are local rather than universal. Their effects weaken with distance, leaving much of the interstellar medium in relatively cold conditions. Astronomers study these environments using radio telescopes, infrared observatories, optical instruments, and space-based detectors sensitive to wavelengths invisible to human eyes. Different forms of radiation reveal different components of the interstellar medium. Together, these observations provide a detailed picture of a galaxy that is not merely a collection of stars but also an intricate network of gas and dust occupying the spaces between them. Within this network, coldness emerges as a natural consequence of scale and density. The energy produced by stars is substantial, but the distances separating those stars are immense. Matter remains sparse. Radiation spreads outward through vast volumes. Energy escapes efficiently into surrounding space. The result is an environment where localized warmth exists around individual stars, while much of the space between them remains cool. The interstellar medium therefore serves as an important bridge between the bright stellar population of a galaxy and the colder regions beyond. It contains the raw material from which future stars and planets will eventually form, yet most of it does not share the intense temperatures of the stars themselves. Instead, it occupies a quieter thermal state shaped by sparse matter, distant radiation sources, and the continual ability of energy to disperse across enormous distances. In these broad spaces between the stars, the cold character of the cosmos becomes increasingly apparent. Within the interstellar medium, some regions become denser than their surroundings. Over immense spans of time, gravity gathers gas and dust into large clouds that drift through galaxies like slow-moving continents. These structures are known as molecular clouds. Many are so thick with dust that they block visible light from stars behind them, appearing as dark patches against brighter backgrounds. Among the coldest natural environments known, molecular clouds and dark nebulae reveal how matter can lose heat and remain sheltered from the warming influence of nearby stars. A molecular cloud forms when gas accumulates into concentrations significantly denser than the surrounding interstellar medium. Hydrogen remains the dominant ingredient, but unlike the more diffuse gas between the stars, much of the hydrogen exists in molecular form. A molecule is created when atoms join together through chemical bonds. In these clouds, pairs of hydrogen atoms combine to form molecular hydrogen. Other molecules also appear, including water, carbon monoxide, ammonia, and a wide variety of more complex substances. The existence of molecules provides an important clue about temperature. Many chemical bonds cannot survive in intensely hot environments. The presence of abundant molecules indicates that these clouds have cooled considerably. Observations show that temperatures within many molecular clouds are only a few tens of degrees above absolute zero. Some of the coldest regions approach even lower values. The darkness of these clouds contributes directly to their coldness. Dust grains mixed with the gas absorb and scatter incoming starlight. As a result, much of the energetic radiation that might otherwise warm the interior is blocked before it can penetrate deeply into the cloud. The outer layers intercept much of the incoming energy, leaving the inner regions shielded from strong external heating. This shielding effect resembles the way dense tree cover can create cooler conditions beneath a forest canopy during a sunny day. In molecular clouds, however, the process occurs on vastly larger scales and with far greater effectiveness. thick concentrations of dust prevent much of the surrounding radiation from reaching the cloud's interior. Protected from intense stellar energy, the gas gradually settles into extremely low temperatures. Cooling mechanisms operate continuously within these environments. Atoms, molecules, and dust grains absorb energy and later release it as radiation. Because space surrounding the cloud remains open, this radiation can escape. Over long periods, the cloud loses thermal energy. The balance between incoming and outgoing radiation determines its temperature. In many cases, energy escapes more readily than it arrives, allowing the cloud to remain remarkably cold. Dark nebulae represent especially dramatic examples of this process. A nebula is a cloud of gas and dust in space. When a cloud blocks light from more distant stars, it appears as a dark silhouette against a brighter background and is often called a dark nebula. These structures can stretch across dozens or even hundreds of light years. To human eyes, they would not appear as glowing objects, but as immense regions of darkness embedded within the star-filled sky. Astronomers study these clouds using wavelengths capable of penetrating dust. Visible light often cannot pass through the dense material, but radio waves and infrared radiation provide valuable information about the hidden interior. Observations reveal a rich environment filled with filaments, knots, and clumps of gas. Despite their quiet appearance, these clouds are dynamic structures shaped by gravity turbulence, magnetic fields, and radiation. One of the most remarkable characteristics of molecular clouds is their role as stellar nurseries. Within particularly dense regions, gravity slowly pulls matter inward. As material accumulates, certain pockets become increasingly concentrated. Over long periods, these dense cores may eventually give rise to new stars. Yet before that transformation occurs, the cloud remains largely defined by cold conditions. The low temperatures are not merely incidental. They help enable the process of gravitational collapse. Hot gas resists compression because rapidly moving particles push outward. Colder gas moves more slowly and offers less resistance. By cooling efficiently, molecular clouds create conditions that allow gravity to gather matter into denser structures. Thus, coldness becomes an essential part of the cycle through which new stars emerge. The scale of these clouds is extraordinary. A single molecular cloud may contain enough material to create thousands of stars. Yet despite this enormous mass, the matter remains spread across volumes so vast that average densities stay extremely low by terrestrial standards. Even in dense regions, the gas would seem almost empty compared with anything encountered on Earth. The absence of strong heating sources within many parts of these clouds further reinforces their cold nature. Nearby stars may illuminate the outer edges, producing faint glows visible in astronomical images. Deep within the interior, however, darkness dominates. Dust blocks incoming radiation, while cooling processes continue to remove energy. The result is an environment where temperatures remain among the lowest found within galaxies. Modern observatories have detected an astonishing variety of molecules within molecular clouds. Some are simple combinations of a few atoms, others are significantly more complex. The existence of these molecules demonstrates how cold and stable certain regions can become. Many of the chemical processes occurring within these clouds would be impossible in hotter environments where energetic radiation constantly breaks molecular bonds apart. From a thermal perspective, molecular clouds illustrate a principle that appears repeatedly throughout the universe. Heat is not maintained simply because stars exist somewhere nearby. Energy must actually reach a region and remain there. When radiation is blocked, when matter efficiently emits energy into space, and when dense atmospheres are absent, temperatures can fall dramatically. Even within a galaxy containing hundreds of billions of stars, pockets of extraordinary coldness can persist. These clouds therefore stand as some of the clearest examples of why the cosmos remains cold across much of its volume. They occupy regions surrounded by starlight, yet their interiors remain shielded. They contain the raw material for future stars, yet they are defined by low temperatures rather than intense heat. Within their dark interiors, gas and dust drift slowly through an environment shaped by isolation, radiation loss, and the quiet persistence of cosmic cold. Scattered throughout galaxies are ordinary stars, luminous spheres of hot gas that transform matter into energy deep within their interiors. These stars are the most familiar sources of light and warmth in the universe. Their brightness dominates the night sky, and their radiation shapes the environment surrounding them. Yet even within regions populated by stars, most of space remains surprisingly cold. The neighborhood of ordinary stars reveals how heat is concentrated near its source, while vast surrounding volumes receive only a small fraction of that energy. A star forms when gravity gathers sufficient gas into a dense central region. As matter falls inward, pressure and temperature rise. Eventually, conditions become extreme enough for nuclear fusion to begin. Fusion is the process through which lighter atomic nuclei combine to form heavier ones, releasing energy in the process. This energy travels outward through the star and eventually escapes into space as radiation. The Sun provides a nearby example. Every second, enormous quantities of energy leave its surface and spread through the solar system. The amount is so large that only a tiny fraction reaches Earth, yet that small fraction powers weather systems, drives ocean circulation, supports ecosystems, and sustains nearly all life at the planet's surface. From a human perspective, the Sun appears overwhelmingly powerful. Yet the influence of a star changes rapidly with distance. Radiation spreads outward in all directions. As it expands, the same quantity of energy occupies an ever-growing volume of space. Consequently, the amount of energy available within a particular area decreases as distance from the star increases. This simple geometric effect becomes one of the most important reasons why space remains cold. The region immediately surrounding a star experiences the strongest heating. Gas near the stellar surface absorbs intense radiation. Charged particles accelerated by stellar winds stream outward. Magnetic fields influence surrounding matter. Within these nearby zones, temperatures can become extremely high. The environment is shaped directly by the star's energetic output. Farther away, however, conditions change significantly. Even within the same stellar system, the difference can be dramatic. Inner planets generally receive far more energy than distant worlds. Small bodies located at great distances encounter only a tiny fraction of the radiation available closer to the star. The energy continues traveling outward, but it becomes increasingly dispersed. The vast separations between stars reinforce this pattern. In a typical region of a galaxy, neighboring stars are not located a few kilometers apart, or even a few billion kilometers apart. They are separated by distances measured in light years. Between them stretches an enormous volume of relatively empty space. Radiation from multiple stars overlaps throughout the galaxy, but the contribution from any individual star becomes weak at large distances. Astronomers often describe stars as occupying only a tiny fraction of a galaxy's total volume. This statement reflects a fundamental aspect of cosmic structure. A galaxy may contain hundreds of billions of stars, yet the space separating those stars remains so immense that most locations are not close to any significant heat source. Bright points of energy exist throughout the galaxy, but they are embedded within an environment dominated by emptiness. The temperature of matter near a star depends on several factors. Distance is crucial, but composition also matters. Dark surfaces absorb more radiation than reflective ones. Atmospheres can trap energy and redistribute heat. Dust and gas clouds may block incoming light. Nevertheless, distance remains the primary factor governing how much stellar energy reaches a particular location. Observations of planetary systems throughout the galaxy reveal this principle repeatedly. Worlds located close to their stars often experience intense heating. Others orbit at greater distances and remain much colder. Some wander through space without orbiting any star at all. These isolated objects receive little external radiation and gradually cool over time. The diversity of temperatures found among planets and smaller bodies reflects the varying influence of stellar energy across different environments. Stars themselves also differ greatly from one another. Some are larger and more luminous than the Sun. Others are smaller and dimmer. Massive stars release enormous quantities of radiation, while low-mass stars emit far less. Yet regardless of their size, all stars share a common limitation. Their energy spreads outward through space and becomes progressively diluted with distance. This dilution helps explain why even a galaxy filled with stars remains largely cold. The combined luminosity of billions of stars is impressive, but it does not create a uniformly warm environment. Instead, each star generates a local zone of influence. These zones overlap in certain regions but remain separated across much of the galactic volume. Between them lie extensive areas where radiation levels remain relatively low. The solar system offers a useful illustration. Earth receives enough solar energy to maintain liquid water and a relatively stable climate. Beyond the orbit of the outer planets, however, solar radiation becomes far weaker. Icy bodies and distant moons exist in environments where sunlight provides only modest warming. The same star that supports a temperate world also illuminates regions of profound coldness farther away. The existence of stars, therefore, does not eliminate cold conditions in space. Rather, stars create islands of warmth within a much larger sea of low temperatures. Their energy is immense, but the universe is larger still. Radiation travels outward, continuously spreading across expanding volumes, and gradually losing its ability to produce significant heating at great distances. Modern astronomy reveals galaxies as networks of such localized energy sources. Each star shines into surrounding space, influencing nearby matter and contributing to the broader radiation field of the galaxy. Yet the collective effect remains uneven. Warmth gathers near stars while coldness persists across the vast spaces separating them. In the neighborhood of ordinary stars, the hidden physics behind cosmic temperature becomes increasingly visible. Heat is abundant where radiation originates. It weakens as distance grows. The enormous separations between stars ensure that much of a galaxy receives only limited amounts of energy. As a result, even within regions populated by countless luminous suns, the dominant condition across most of space remains cold. Within the solar system, the influence of the sun becomes easier to observe directly. Unlike distant stars scattered across the galaxy, the sun serves as a nearby source of energy whose effects can be measured in detail. Its light illuminates planets, moons, asteroids, and comets. Its radiation drives atmospheric processes, influences surface temperatures, and shapes the conditions experienced throughout the planetary system. Yet even here, within the domain of a powerful star, space itself remains cold. The journey of sunlight through the solar system reveals why. The Sun is an ordinary star in many respects, yet its scale remains immense when compared with human experience. Deep within its interior, nuclear fusion converts hydrogen into helium, releasing extraordinary amounts of energy. This energy gradually moves outward through the Sun before escaping into space as electromagnetic radiation. Visible light forms only a small portion of that radiation. The Sun also emits infrared energy, ultraviolet radiation, and other forms of electromagnetic waves. Once released, this energy begins a journey outward in all directions. Unlike sound, which requires a material medium through which to travel, electromagnetic radiation can move through empty space. This ability allows sunlight to cross the vast vacuum separating the Sun from the planets. Without it, the solar system would remain a dark and frozen collection of worlds. At Earth's distance from the Sun, enough energy arrives to support a relatively warm planetary environment. Oceans remain liquid over much of the surface. Atmospheric circulation transports heat around the globe. Life thrives because a continuous stream of solar energy reaches the planet. Yet Earth occupies only one location within a much larger system. As sunlight travels farther from its source, it spreads across an ever-expanding area. The total amount of energy leaving the Sun remains constant, but that energy becomes distributed across larger and larger spheres centered on the Sun. Consequently, each square meter located farther away receives less energy than a square meter closer to the source. This decrease occurs steadily throughout the solar system. The planet Mercury receives far more solar energy than Earth because it orbits much closer to the Sun. Venus also receives intense radiation. By contrast, Mars receives significantly less. The giant planets farther outward encounter even weaker sunlight. Beyond them, the reduction becomes increasingly dramatic. A useful comparison involves a lantern shining across an open field at night. Near the lantern, the light appears bright and concentrated. Farther away, the illumination weakens. At great distances, only a faint glow remains visible. The lantern continues emitting the same amount of light, but that light becomes spread across a wider area. Sunlight behaves similarly, though on a vastly larger scale. The vacuum of space plays an important role in this process. Between planets, there is no dense atmosphere capable of trapping large amounts of heat. Radiation travels freely outward. Objects exposed to sunlight absorb some of that energy and warm. At the same time, they emit energy back into space. Their temperatures depend on the balance between incoming and outgoing radiation. Earth's atmosphere modifies this balance. Certain gases absorb and re-emit infrared radiation, helping retain some of the heat received from the Sun. Without this effect, Earth's average surface temperature would be much lower. The Moon provides a useful contrast. Lacking a substantial atmosphere, it experiences extreme temperature differences between day and night. Sunlit regions become hot, while shaded regions cool rapidly. This contrast demonstrates an important principle. Space itself is not warm simply because sunlight passes through it. Radiation transports energy through the vacuum, but the vacuum does not store that energy in the way air, water, or solid matter can. An object must absorb sunlight in order to warm significantly. Empty space between objects remains largely unaffected. Astronauts operating outside spacecraft experience this reality directly. A person in sunlight receives intense radiation from the Sun. At the same time, the surrounding vacuum remains incapable of transferring heat through direct contact. Thermal conditions depend strongly on exposure to sunlight, the properties of the spacesuit, and the ability to emit excess energy back into space. The solar system contains many examples of how sunlight weakens with distance. Asteroids located between Mars and Jupiter generally receive less solar energy than Earth. The giant planets orbit even farther away. Jupiter, despite its enormous size, receives only a fraction of the sunlight that reaches Earth. Saturn receives less still. Uranus and Neptune exist in regions where solar illumination becomes faint compared with conditions near the inner planets. Yet even at these great distances, sunlight remains present. The Sun can still be seen shining in their skies. The key difference lies in intensity. The energy arriving at these remote worlds is much smaller than the amount reaching planets closer to the Sun. As a result, temperatures tend to be lower, especially in regions lacking substantial internal heat sources. The outward journey of sunlight therefore reveals an important truth about cosmic temperature. The sun produces extraordinary amounts of energy, but that energy does not fill the solar system uniformly. It spreads across increasing volumes of space, becoming less concentrated with distance. Objects close to the sun absorb large amounts of radiation. Objects farther away absorb much less. Throughout the solar system, warmth is tied not merely to the existence of the sun, but to the amount of solar energy that actually reaches a particular location. Empty space allows radiation to travel efficiently, yet it does not preserve concentrated heat across immense distances. As sunlight expands outward from its source, its influence gradually weakens. The result is a planetary system containing both relatively warm environments and profoundly cold ones, all illuminated by the same star. The sun remains a powerful engine of energy, but the vast distances separating the worlds ensure that its warmth diminishes steadily as radiation spreads through space. Even within its own domain, the hidden physics of distance and energy distribution maintain the cold character of much of the surrounding cosmos. Far beyond the region occupied by the inner planets, the solar system enters a realm where sunlight becomes increasingly faint and cold. Conditions dominate. The outer solar system contains giant planets, icy moons, dwarf planets, comets, and vast populations of frozen objects orbiting at tremendous distances from the sun. These distant regions provide some of the clearest examples of how a powerful star can illuminate an enormous volume of space while leaving much of it extremely cold. The transition begins gradually. Beyond Mars lies a broad zone populated by countless rocky bodies known as the asteroid belt. Although many asteroids remain cold compared with Earth, they still receive measurable amounts of sunlight. Farther outward, however, the reduction in solar energy becomes increasingly significant. The giant planets occupy distances where the sun appears smaller in the sky, and where each square meter receives only a fraction of the radiation available nearer the center of the solar system. Jupiter is the first of these giant worlds. Even at its great distance, it remains brightly illuminated by the sun. Yet the amount of solar energy reaching Jupiter is far lower than the amount arriving at Earth. A person standing above Jupiter's cloud tops, if such a location were possible, would see a sun that appears noticeably smaller and less intense. The reduction results entirely from distance. The sun continues emitting the same amount of energy, but that energy has spread across a much larger region of space before reaching Jupiter. Beyond Jupiter lies Saturn, surrounded by its famous rings. At Saturn's orbit, sunlight weakens further. The planet and its moons remain illuminated, but the energy arriving from the sun is much less concentrated. Temperatures throughout the Saturnian system reflect this reduced solar influence. Ice becomes increasingly common. Frozen compounds that would quickly evaporate closer to the sun remain stable in these colder environments. Farther still orbit Uranus and Neptune. These distant planets occupy regions where sunlight has become remarkably faint, compared with conditions experienced on Earth. Daylight still exists, yet the energy available for warming surfaces and atmospheres is greatly diminished. The sun appears as a bright star-like disk rather than the dominant presence familiar from the inner solar system. Despite receiving limited solar energy, some outer planets and moons exhibit signs of internal heat. Jupiter, Saturn, and Neptune release more energy than they receive from sunlight. This additional energy originates from processes within the planets themselves, including the slow release of heat retained from their formation and the gradual compression of material under immense gravitational forces. Internal heat can influence atmospheric activity and local conditions, but it does not alter the broader reality that these worlds inhabit a cold region of the solar system. Many moons in the outer solar system are covered with extensive ice. Water ice, which is relatively uncommon on Earth's surface outside polar and high-altitude environments, becomes widespread. Other frozen substances also appear. Methane, nitrogen, ammonia, and carbon dioxide can exist as solids under the low temperatures found in these distant regions. The abundance of ice serves as visible evidence of the weak solar heating available so far from the Sun. One of the most intriguing examples is the dwarf planet Pluto. Orbiting at an average distance far beyond Neptune, Pluto receives only a tiny fraction of the sunlight that reaches Earth. The weak solar radiation supports temperatures low enough for exotic ices to persist on its surface. Nitrogen and methane, which are gases under ordinary conditions on Earth, can freeze into solid layers across portions of Pluto's landscape. Beyond Pluto extends a vast population of icy bodies often referred to as the Kuiper Belt. This region contains remnants from the early formation of the solar system. Many of these objects spend their existence in environments where sunlight provides only minimal warming. Their surfaces preserve frozen materials that would be unstable closer to the Sun. Farther outward still lies an even larger realm known as the Oort cloud, a hypothetical but widely accepted reservoir of comets surrounding the solar system. Although direct observations remain limited, evidence suggests that this distant cloud may extend thousands of times farther from the Sun than Pluto's orbit. At such extraordinary distances, solar energy becomes exceedingly weak. The Sun would appear as a bright star rather than a dominant source of illumination. The outer solar system demonstrates an important principle about temperature. Heat depends not only on the existence of an energy source, but also on proximity to that source. The Sun remains enormously powerful throughout the entire solar system. Yet because its radiation spreads outward through expanding volumes of space, distant objects receive progressively less energy. The result is a steady transition toward colder conditions. These remote regions also reveal how effectively objects can retain low temperatures when external heating is limited. Ice remains stable over billions of years. Frozen landscapes persist with little change. Chemical compounds that exist only briefly in warmer environments can survive for immense spans of time. The cold conditions become part of the long-term character of these worlds. Observations from spacecraft have transformed scientific understanding of the outer solar system. Missions exploring Jupiter, Saturn, Uranus, Neptune and Pluto reveal environments of remarkable complexity. Storms, geological activity, subsurface oceans and intricate atmospheric processes exist even in regions receiving weak sunlight. Yet beneath this diversity lies a common thermal reality. These worlds occupy a realm where solar energy has become diluted across enormous distances. The farther one travels from the Sun, the more clearly the cold nature of space reveals itself. Sunlight continues its outward journey, but its intensity steadily declines. Empty space does not preserve concentrated warmth. Radiation spreads, energy disperses, and temperatures fall. The outer solar system therefore stands as a vast demonstration of the hidden physics governing cosmic coldness. Even within the reach of a powerful star, distance alone can transform illuminated worlds into places defined by ice, darkness, and enduring cold. Among the many worlds orbiting the Sun, Earth occupies a particularly unusual position. It exists within a cosmic environment that is fundamentally cold, yet its surface supports liquid oceans, active weather systems, and a vast diversity of living organisms. Compared with most known locations in the solar system, Earth is relatively warm. Understanding this warmth provides an important contrast to the surrounding coldness of space, and reveals why the presence of a nearby star alone does not fully explain planetary temperature. Earth receives a continuous flow of energy from the Sun. Every day, sunlight reaches the planet after crossing approximately 150 million kilometers of space. This incoming radiation supplies the energy that drives nearly every major process occurring at the surface. Winds, clouds, rainfall, ocean currents, and biological activity all depend directly or indirectly on solar energy. The amount of sunlight arriving at Earth is neither excessively large nor excessively small. Mercury receives far more solar radiation, while Mars receives less. Earth's distance from the Sun places it within a range where water can exist naturally in liquid form across much of the surface. This condition has profound consequences because liquid water stores, transports, and redistributes heat efficiently. The oceans cover most of Earth's surface and act as enormous thermal reservoirs. During periods of strong sunlight, ocean water absorbs large quantities of energy. Rather than allowing temperatures to rise immediately to extreme levels, the water stores much of this energy and releases it gradually over time. This process helps moderate daily and seasonal temperature variations. The atmosphere provides another crucial layer of thermal regulation. Unlike the vacuum of space, Earth's atmosphere contains vast numbers of gas molecules. These molecules interact continuously with incoming and outgoing radiation. Some gases absorb portions of the infrared energy emitted by the planet's surface and then re-emit that energy in various directions. As a result, part of the outgoing energy remains within the lower atmosphere rather than escaping directly into space. This process is commonly known as the greenhouse effect. It occurs naturally and is essential for maintaining Earth's relatively warm climate. Without it, the average surface temperature would be substantially lower. Liquid water would become far less common, and many of the environmental conditions associated with life would be dramatically different. The atmosphere also distributes heat across the planet. Air masses move from one region to another through large-scale circulation patterns. Warm air rises, cool air descends, and winds transport energy across vast distances. Oceans perform a similar function. Currents carry warm water toward colder regions and return cooler water toward warmer latitudes. Together, these systems help prevent extreme temperature differences between many parts of the world. Earth's surface characteristics further influence temperature. Land water, ice forests, deserts, and clouds absorb and reflect different amounts of solar radiation. Darker surfaces generally absorb more energy, while brighter surfaces reflect more. Snow and ice, for example, reflect a significant portion of incoming sunlight back towards space. Oceans absorb much more. The combination of these surfaces creates a complex and dynamic thermal environment. Yet despite all these warming influences, Earth remains surrounded by cold space. The boundary between the atmosphere and the vacuum beyond represents a sharp transition. Above the atmosphere there is no dense medium capable of storing and transporting heat through the same mechanisms found near the surface. Spacecraft orbiting Earth experience conditions fundamentally different from those at sea level. Astronauts aboard orbiting stations observe this contrast directly. One side of a spacecraft may face the sun and receive intense radiation. Another side may face deep space and lose energy through radiation. Managing these thermal differences requires careful engineering. The surrounding vacuum neither warms nor cools through direct contact in the manner of air or water. Instead, radiation becomes the dominant method of energy exchange. Earth itself continuously emits energy back into space. The planet absorbs solar radiation and later releases energy in the form of infrared radiation. Over long periods, a balance exists between the energy received and the energy emitted. If Earth absorbed significantly more energy than it released, temperatures would continue rising. If it emitted much more than it absorbed, temperatures would decline. The relative stability of the climate depends on this ongoing balance. The Moon provides an illuminating comparison. Located nearly the same distance from the Sun as Earth, the Moon receives almost identical amounts of solar radiation. Yet its thermal behavior differs dramatically because it lacks a substantial atmosphere and large oceans. Sunlit lunar surfaces become extremely hot during the lunar day, while temperatures plunge during the long lunar night. Earth avoids such extremes largely because of its atmosphere and oceans. This comparison reveals an important lesson. Solar energy alone does not determine a world's temperature. The ability to absorb, store, transport, and retain that energy matters just as much. Earth's warmth results from a combination of favourable distance from the sun, abundant liquid water, atmospheric insulation, and active circulation systems. Viewed from space, Earth appears as a bright and comparatively warm oasis embedded within a much colder environment. The planet intercepts a small fraction of the sun's radiation and uses that energy to maintain conditions very different from those found across much of the solar system. Yet even this warmth remains temporary and dependent on a continual supply of incoming solar energy. The broader cosmos surrounding Earth remains dominated by coldness. The atmosphere protects the surface from experiencing the full thermal reality of space. Oceans store heat, winds distribute energy, clouds regulate radiation. These features create an environment where warmth can persist. Without them, Earth would more closely resemble the colder world scattered throughout the solar system. Earth therefore serves as a reminder that warmth in the universe is often a local achievement rather than a universal condition. The planet remains relatively warm, not because space itself is warm, but because specific physical processes capture and manage a small portion of the energy arriving from the sun. Against the backdrop of a cold cosmos, Earth stands as a rare example of how distance, atmosphere, water, and energy balance can work together to create a comparatively temperate world. After examining the regions shaped by stars, planets, gas clouds, and sunlight, attention turns toward one of the most important physical realities underlying the temperature of space itself, the vacuum. The word is often used casually to describe emptiness, yet in physics it has a more precise meaning. A vacuum is a region containing extremely little matter. Understanding the nature of a vacuum is essential because it explains why the coldness of space behaves so differently from the coldness experienced on Earth. Human experience develops almost entirely within environments filled with matter. Air surrounds every person at the surface of Earth. Water fills oceans, rivers, and lakes. Solid materials form landscapes, buildings, and living organisms. In all these environments, particles are abundant. Molecules constantly collide, exchange energy, and transfer heat from one location to another. The vacuum of space is fundamentally different. Beyond Earth's atmosphere, the number of particles decreases dramatically. Even in regions that contain gas and dust, matter remains extraordinarily sparse compared with terrestrial conditions. Large portions of space contain so few particles that they would be considered far emptier than any vacuum chamber ever produced in a laboratory. This scarcity of matter changes the way temperature is experienced. On Earth, a cold winter day feels cold because air molecules continually collide with exposed skin and carry energy away. A hot summer day feels warm because energetic molecules transfer heat toward the body. In both cases, direct contact between matter and matter allows energy to move efficiently. In a vacuum, that process becomes almost impossible. With very few particles present, there are very few collisions. Without frequent collisions, energy cannot flow through direct contact in the familiar way. This distinction is one of the most important reasons why space remains difficult to understand using everyday intuition. When people imagine space as cold, they often picture it behaving like icy air. In reality, the vacuum itself does not function as a cold substance surrounding objects. It is better understood as an environment largely lacking the material needed for ordinary heat transfer. The sensation of cold associated with space arises from how objects lose energy within that environment, rather than from the vacuum actively cooling them through contact. A useful comparison comes from considering a thermos flask designed to keep beverages warm. Many thermos containers include a layer where much of the air has been removed. The resulting vacuum reduces heat transfer because fewer particles remain available to carry energy from the warm liquid to the outside environment. The vacuum acts as an insulator. Space operates according to the same principle on a vastly larger scale. This fact often surprises people. A vacuum is not inherently efficient at removing heat. In many situations, it actually slows certain forms of heat transfer. Without air or another material medium, energy cannot move through conduction, the process by which neighboring particles pass energy directly to one another. The absence of matter eliminates most opportunities for such exchanges. The sparse particles that do exist in space generally contribute very little to thermal interactions. A spacecraft orbiting Earth, for example, encounters only tiny amounts of atmospheric material at high altitudes. The surrounding environment contains far too few particles to produce significant heating or cooling through direct contact. Instead, another process dominates the spacecraft's thermal behavior. The concept of temperature itself becomes somewhat more subtle in a vacuum. Temperature usually refers to the average energy of particles. In a region containing very few particles, assigning a temperature remains possible, but the practical meaning changes. A handful of energetic particles may correspond to a high measured temperature while carrying only a tiny amount of total energy. Conversely, a region may contain radiation associated with low temperatures, even though few particles are present. This distinction explains why some parts of space can contain gas measured at thousands or millions of degrees, while still being unable to warm nearby objects significantly. The particles possess considerable energy individually, but there are so few of them that the total energy available remains limited. The vacuum prevents efficient transfer of that energy through direct contact. The environment surrounding Earth offers a clear demonstration. Satellites orbit through space where particle densities are extremely low. Yet these satellites do not immediately assume the temperature of the surrounding vacuum. Instead, their temperatures depend primarily on exposure to sunlight reflection from Earth and the rate at which they emit radiation into space. The vacuum itself contributes relatively little through direct thermal contact. Astronauts conducting activities outside spacecraft experience the same reality. A spacesuit must provide insulation, temperature regulation, and protection from solar radiation. The challenge is not simply surviving in a cold environment, it is managing energy in a setting where ordinary atmospheric heat transfer is largely absent. Exposure to sunlight can produce heating, while shaded surfaces may lose energy steadily through radiation. Modern engineering relies heavily on this understanding. Spacecraft employ reflective coatings, insulation layers, radiators, and thermal control systems specifically because the vacuum changes the rules governing temperature. Designs that function effectively on Earth often require major modification before they can operate in space. The vacuum also helps explain why cold conditions can persist across much of the universe. Since matter is sparse, heat cannot spread easily through conduction or large-scale contact between particles. Energy sources such as stars remain localized. Their radiation travels across space, but the vacuum prevents warmth from diffusing outward in the same manner that heat spreads through air or water. In this way, the vacuum acts as a stage upon which cosmic temperature unfolds. It does not actively create coldness, nor does it behave like a frozen substance surrounding celestial objects. Instead, it limits certain pathways through which energy might otherwise move. By removing most of the matter required for direct thermal exchange, the vacuum ensures that heat remains concentrated near its sources, while much of the surrounding universe retains its cold character. The emptiness of space therefore carries profound consequences. It shapes how planets warm, how spacecraft operate, how stars influence their surroundings, and how energy travels across cosmic distances. The coldness of the universe is inseparable from the reality of the vacuum, an environment where matter becomes so rare that many of the familiar rules governing heat on Earth no longer apply. To understand fully why space remains cold despite the tremendous energy produced by stars, it is necessary to examine the ways heat actually moves. On Earth, energy travels through several familiar mechanisms that operate continuously in everyday life. Warm hands transfer heat to a cold object. Boiling water circulates energy through motion. Sunlight warms a surface from a distance. These processes may seem ordinary, yet they reveal a fundamental principle. Heat does not simply exist in one place and then appear somewhere else. It must be transported through specific physical pathways. In physics, three primary methods transfer thermal energy. These are conduction, convection, and radiation. Each operates according to different rules. Together they explain why some environments become warm while others remain cold. They also reveal why the vacuum of space behaves so differently from the atmosphere surrounding Earth. Conduction occurs when particles transfer energy directly through contact. Imagine placing a metal spoon into a pot of hot water. The portion submerged in the water becomes warm first. Gradually the heat spreads through the spoon until the handle also becomes warm. This process occurs because energetic particles collide with neighboring particles and pass along some of their energy. Conduction functions efficiently in solids because particles are packed relatively close together. It also occurs in liquids and gases, although generally less effectively. On Earth, conduction contributes to countless thermal interactions. Warm ground heats the air touching it. Human skin exchanges energy with clothing. Buildings lose heat through walls and windows. Direct contact allows energy to move from warmer regions toward cooler ones. The effectiveness of conduction depends strongly on the presence of matter. Without particles available to collide, the process cannot operate. This limitation becomes crucial in space. The vacuum contains so little matter that opportunities for direct energy exchange are extremely rare. Consequently, conduction contributes very little to temperature changes across most cosmic distances. A second mechanism, convection, involves the movement of fluids. In physics, a fluid refers to substances capable of flowing, including liquids and gases. When a fluid is heated, warmer portions often become less dense and rise while cooler portions descend. This motion transports energy from one location to another. A pot of water heating on a stove provides a familiar example. Water near the bottom receives energy first. As it warms, it rises. Cooler water sinks to replace it. The resulting circulation distributes heat throughout the container. Earth's atmosphere behaves similarly. Warm air rises from sunlit surfaces while cooler air descends elsewhere. Wind storms and large-scale weather systems all depend upon convection. The oceans also transport energy through convective processes. Warm currents carry heat across thousands of kilometers. Cold currents return cooler water toward lower latitudes. These movements help moderate regional climates and influence weather patterns around the globe. Like conduction, convection requires matter. A fluid must be present and capable of movement. In the vacuum of space, no widespread atmosphere or ocean exists through which such circulation can occur. Large-scale convective transport therefore becomes impossible across most cosmic environments. Heat cannot spread through space in the same manner that warmth spreads through air or water on Earth. The absence of conduction and convection in the vacuum fundamentally alters the thermal behavior of the cosmos. Two of the most familiar methods of heat transfer become largely unavailable, yet energy still travels across space. The warmth felt from sunlight demonstrates this reality. The remaining mechanism responsible is radiation. Radiation differs from the other two processes because it does not require matter. Instead, energy travels in the form of electromagnetic waves. Visible light represents one portion of this spectrum. Infrared radiation, ultraviolet radiation, radio waves, microwaves, and X-rays belong to the same broader family. The Sun provides a constant example of radiative energy transfer. Between Earth and the Sun lies nearly 150 million kilometers of mostly empty space. Neither conduction nor convection can transport energy across this distance. Yet sunlight arrives continuously because electromagnetic radiation can travel through a vacuum. This ability makes radiation uniquely important in astronomy. Nearly every observation of the universe depends upon detecting electromagnetic waves, emitted, reflected, or absorbed by distant objects. Stars shine through radiation. Galaxies become visible through radiation. Even the ancient glow of the cosmic microwave background reaches observers through radiation. Radiation also governs how objects gain and lose energy in space. A planet illuminated by a star absorbs incoming radiation. Its surface warms. At the same time, the planet emits radiation back into space. The balance between absorption and emission determines its temperature. Similar principles apply to moons, asteroid spacecraft, and nearly every other object exposed to the vacuum. Because radiation operates over great distances, it might appear capable of warming all of space. However, another important factor intervenes. As radiation moves away from its source, it spreads across increasingly large regions. The total energy remains the same, but it becomes distributed over a greater area. Consequently, the intensity decreases with distance. This spreading effect explains why planets farther from the Sun receive less energy. It also explains why most of interstellar and intergalactic space remains cold. Radiation travels efficiently through the vacuum, yet its energy becomes progressively diluted as it expands outward. The contrast between Earth and space becomes especially clear when viewed through the lens of these three mechanisms. On Earth, conduction, convection, and radiation all operate simultaneously. Warmth can move through solid materials, circulate through air and water, and arrive from the Sun. In space, conduction and convection largely disappear across large distances. Radiation remains the dominant pathway. The result is a universe where heat tends to remain concentrated near its sources. Stars generate enormous quantities of energy, but only radiation can carry that energy outward through the vacuum. As the radiation spreads, its intensity decreases. Without atmospheres, oceans, or dense materials filling the cosmos, there are few alternative routes through which warmth can propagate. Understanding these pathways reveals why coldness persists throughout so much of the universe. The issue is not a lack of energy production. Stars, galaxies, and other cosmic phenomena generate extraordinary amounts of energy. Rather, the structure of space limits how that energy can move. With conduction and convection largely absent across cosmic distances, radiation alone must perform the task. As it spreads through the immense emptiness of the cosmos, much of space remains cold despite the brilliance of the stars. Radiation is the great messenger of the universe. It carries energy from stars to planets, from distant galaxies to telescopes, and from the earliest observable stages of cosmic history to the present day. Unlike conduction and convection, radiation does not require matter to exist between its source and destination. Because most of the universe consists of vast stretches of near-empty space, radiation becomes the primary method through which energy travels across cosmic distances. Understanding radiation reveals why sunlight can warm a planet while leaving much of space itself cold. At its most fundamental level, radiation consists of electromagnetic waves. These waves carry energy and move through space at the speed of light. Human eyes detect only a small portion of the electromagnetic spectrum known as visible light. Beyond visible light lie infrared radiation, ultraviolet radiation, radio waves, microwaves, X-rays, and gamma rays. All are forms of the same underlying phenomenon. The Sun continuously emits electromagnetic radiation across many wavelengths. Some of this energy arrives at Earth and warms the planet. Other portions travel outward toward the outer solar system and beyond. The radiation does not need air, water, or any other material medium, it simply moves through the vacuum. This property makes radiation unique among the mechanisms of heat transfer. A campfire can warm a nearby person through radiation, even though the surrounding air also contributes through convection. Sunlight reaches Earth almost entirely through radiation. Without this process, the vacuum separating the Sun from the planets would prevent the transfer of significant amounts of energy. The relationship between radiation and temperature is closely connected. Every object with a temperature above absolute zero emits electromagnetic radiation. Hotter objects generally emit more energy and often radiate at shorter wavelengths. Cooler objects emit less energy and radiate primarily at longer wavelengths. A heated metal object provides an everyday example. As its temperature rises, it begins emitting visible light. At first, it glows a dull red. With increasing temperature, the glow becomes brighter and shifts toward orange-yellow and eventually white. The changing color reflects changes in the distribution of emitted radiation. Stars follow the same principles. Their temperatures determine both the amount and character of the radiation they emit. Hot stars produce large quantities of high-energy radiation. Cooler stars emit less energetic radiation. The Sun occupies an intermediate range, producing substantial visible light along with other wavelengths. Once radiation leaves its source, it spreads outward. This spreading is one of the most important concepts in understanding cosmic temperature. Imagine a small lamp illuminating a dark room. Near the lamp, the light appears bright because a large fraction of the emitted energy passes through a relatively small area. Farther away, the same energy becomes distributed across a larger area, making the illumination weaker. The same principle applies to stars. The Sun emits an enormous amount of energy, but that energy expands outward in all directions. As the distance from the Sun increases, the energy becomes spread across increasingly large spherical surfaces. Consequently, each square meter located farther away receives less energy than one located closer to the Sun. This geometric spreading explains why planets near the Sun tend to be warmer than those farther away. It also explains why most of the space between planets remains cold. Radiation is present throughout the solar system, but its intensity varies dramatically with distance. Empty space does not accumulate this energy in the way that matter can. An important distinction emerges here. Radiation travels through space, but space itself does not store large amounts of thermal energy, simply because radiation passes through it. A beam of sunlight crossing a vacuum carries energy, yet the vacuum remains largely unchanged. For significant warming to occur, an object must absorb the radiation. Earth absorbs a portion of the sunlight reaching it. Oceans, land surfaces, clouds, and atmospheric gases interact with incoming radiation. Some energy is reflected, some is absorbed, and some is later emitted back into space. These interactions create the temperatures experienced at the planet's surface. A similar process occurs throughout the universe. Dust grains absorb starlight and warm slightly before re-radiating energy at longer wavelengths. Gas clouds absorb certain forms of radiation and later emit their own characteristic radiation. Planets and moons absorb energy from nearby stars and radiate heat into space. Everywhere, radiation serves as the medium through which energy is exchanged. The cosmic microwave background provides another important example. This faint radiation fills all directions of space and represents a remnant of the early universe. Although extremely weak compared with sunlight, it demonstrates that radiation can persist across immense spans of time and distance. Every location in the observable universe is immersed within this ancient glow. Yet despite the omnipresence of radiation, the universe remains mostly cold. The reason lies in the distribution of energy. Radiation exists everywhere, but it is usually sparse. Most regions are far from powerful sources such as stars. The energy passing through any given volume is therefore relatively small. Radiation can travel across the cosmos, but the immense size of the universe ensures that much of it remains thinly spread. This reality becomes especially apparent in interstellar and intergalactic space. Radiation from countless stars and galaxies crosses these regions continuously. Nevertheless, the distances involved are so enormous that the combined energy density remains low. The result is an environment where light exists yet temperatures remain cold. Modern astronomy depends entirely upon radiation. Every image of a galaxy, every measurement of a distant star, and every observation of a nebula relies on electromagnetic waves reaching instruments on Earth or in space. Radiation not only transfers energy, but also carries information. Through it, astronomers learn about the temperature, composition, motion, and history of objects across the universe. As a mechanism of heating, radiation possesses extraordinary reach. It can cross millions or even billions of light years. Yet it also possesses an inherent limitation. The farther it travels, the more widely it spreads. The intensity decreases. The warming influence weakens. The universe therefore becomes a place where energy can move freely through empty space, while still remaining insufficiently concentrated to eliminate widespread coldness. Radiation is the bridge connecting stars to the worlds around them and linking distant regions of the cosmos. It allows energy to travel through the vacuum and makes warmth possible far from its source. At the same time, the immense scale of space ensures that this energy becomes diluted across vast distances. Through radiation, the hidden physics of cosmic temperature becomes clear. Light can travel almost anywhere, but concentrated warmth remains rare in a universe whose greatest feature is its enormous size. While radiation allows energy to travel across the vacuum of space, it also provides the mechanism through which objects lose energy. Every planet, moon, asteroid, spacecraft, dust grain, and gas cloud continually emits radiation into its surroundings. This process of radiative cooling plays a central role in shaping temperatures throughout the universe. Understanding how objects cool in darkness reveals why cold conditions are so widespread, and why warmth often remains temporary unless a continual source of energy is available. On Earth, cooling occurs through several pathways. A warm object may transfer energy to the surrounding air through conduction. Moving air may carry that energy away through convection. Radiation also contributes by allowing the object to emit electromagnetic energy into its environment. Because Earth's atmosphere contains abundant matter, all three mechanisms often operate simultaneously. In space, the situation is different. The vacuum largely eliminates conduction and convection across large distances. As a result, radiation becomes the dominant means through which isolated objects lose thermal energy. If an object in space receives less energy than it emits, its temperature gradually declines. This principle applies universally. A warm rock drifting through interplanetary space radiates energy outward in all directions. Unless sunlight or another energy source replenishes the lost energy, the rock cools. The same process affects planets, moons, spacecraft, and even large clouds of gas. Every object continually participates in an exchange between absorbing energy and emitting it. The rate of cooling depends on several factors. Temperature is one of the most important. Hotter objects emit more radiation than cooler ones. Consequently, very warm objects often cool relatively quickly at first. As their temperatures decrease, the rate of energy loss also declines. Over time, they approach a balance with their surroundings. The properties of a surface also matter. Dark surfaces generally absorb radiation efficiently and often emit it efficiently as well. Reflective surfaces may absorb less incoming energy and can behave differently when emitting radiation. Engineers designing spacecraft pay close attention to these characteristics because thermal management becomes essential in the vacuum of space. A spacecraft orbiting Earth illustrates the challenge. One side may face direct sunlight while another faces the darkness of space. Sunlit surfaces absorb energy and warm. Shaded surfaces emit radiation and cool. Without careful design, temperature differences could become extreme. Spacecraft therefore use insulation reflective coatings, radiators and other systems to control how energy is gained and lost. The Moon provides a natural example of radiative cooling. During the lunar day, sunlight warms the surface. When night falls, the absence of a substantial atmosphere allows energy to escape readily through radiation. Temperatures decline dramatically because there is little material available to retain and redistribute heat. The lunar surface demonstrates how rapidly conditions can change when radiation becomes the primary mechanism governing thermal behavior. Asteroids experience similar effects. Many rotate slowly enough that one side remains illuminated for extended periods, while the opposite side spends long intervals in darkness. Sunlit regions warm as they absorb radiation from the sun. Darkened regions cool by emitting energy into space. The resulting temperature contrasts can be substantial. Even entire planets undergo continuous radiative cooling. Earth absorbs energy from the sun and emits infrared radiation into space. The planet's atmosphere influences how efficiently this energy escapes, but the overall process remains essential. Without radiative cooling, temperatures would continue rising as solar energy accumulated. The long-term stability of Earth's climate depends upon balancing incoming and outgoing energy. The same principle applies across the solar system and beyond. Every world, regardless of its composition or location, participates in a thermal balance governed by radiation. Warmth persists only when energy continues arriving from sources such as stars, internal geological activity or other processes. When those inputs decline, cooling follows. The darkness of space contributes significantly to this outcome. In everyday language, darkness often refers simply to the absence of visible light. In thermal terms, darkness frequently indicates the absence of substantial incoming radiation. An object located in darkness may continue emitting energy while receiving little in return. Under such conditions, cooling becomes inevitable. This effect is especially important in regions far from stars. Distant objects in the outer solar system receive only weak sunlight. Their temperatures reflect a balance between limited incoming energy and continual radiative loss. As solar energy decreases with distance, equilibrium temperatures fall. Frozen landscapes become common. Ice remains stable. Cold conditions persist over immense spans of time. Interstellar space provides an even broader example. Dust grains and gas clouds absorb energy from nearby stars, but they also emit radiation continuously. In regions where incoming energy is weak, cooling can dominate. Over long periods, temperatures approach the low values characteristic of much of the interstellar medium. The cosmic microwave background establishes a faint thermal environment present throughout the universe. An isolated object drifting through deep space eventually exchanges radiation with this background. If no significant nearby energy sources exist, the object's temperature gradually approaches the surrounding radiative conditions. This process reflects the tendency of thermal systems to move toward equilibrium. Astronomers observe radiative cooling throughout the cosmos. Hot gas surrounding galaxies emits radiation and gradually loses energy. Expanding remnants of stellar explosions cool as they radiate into space. Molecular clouds remain cold partly because they efficiently emit energy, while receiving limited heating in their shielded interiors. Across a wide range of environments, radiation serves not only as a carrier of heat, but also as a pathway through which heat departs. The widespread coldness of the universe emerges naturally from this continual process. Stars generate enormous quantities of energy, but objects throughout space are constantly radiating energy away. Warmth requires maintenance. Without ongoing heating, cooling gradually reduces temperatures. The vacuum provides little resistance to radiative loss, because conduction and convection contribute minimally across cosmic distances. As a result, the universe contains countless objects engaged in a quiet thermal exchange. Energy arrives, energy departs, and temperatures adjust accordingly. In regions close to powerful sources of radiation, warmth can persist. In regions where incoming energy is weak, cooling dominates. The darkness of space is therefore not merely an absence of light. It is an environment where radiative cooling continually works to remove thermal energy from matter, helping sustain the cold character that defines so much of the cosmos. After moving from the largest scales of the universe through galaxies, interstellar clouds, stars, planets, the vacuum of space, and the physics of heat transfer, the central question becomes clearer. The coldness of space is not a mystery arising from a lack of energy. The universe contains extraordinary sources of power. Stars shine continuously. Galaxies produce immense amounts of radiation. Explosive events release energies that exceed ordinary human comprehension. Yet despite all of this activity, most of space remains cold. The explanation emerges from the combined effects of scale, distance, emptiness, and the way energy moves through the cosmos. The first and perhaps most important factor is the immense size of the universe. Human intuition develops within environments measured in meters and kilometers. Even planetary distances challenge ordinary understanding. Cosmic distances extend far beyond these scales. Stars that appear close together in the night sky are often separated by many light years. Galaxies themselves are divided by millions of light years. Between major cosmic structures lie enormous regions containing very little matter. Because the universe is so vast, energy becomes distributed across extraordinary volumes. A star may emit tremendous amounts of radiation, but that radiation spreads outward in every direction. The farther it travels, the larger the area across which it is distributed. As a result, its intensity decreases with distance. The energy remains present, yet it becomes increasingly diluted. This dilution is not a minor effect. It governs the thermal character of the cosmos. A location near a star may receive enough radiation to warm planets and drive atmospheric activity. A location much farther away may receive only a small fraction of that energy. Since most of the volume of the universe lies far from stars, most regions experience relatively low levels of heating. The vacuum of space reinforces this reality. In everyday environments, heat spreads through conduction and convection. Warm air carries energy from one place to another. Liquids transport heat through circulation. Solid materials transfer energy through direct contact. Space largely lacks the matter required for these processes. Consequently, two major pathways for heat transfer become ineffective across cosmic distances. Radiation remains as the dominant mechanism. It allows energy to travel through empty space, making sunlight possible and enabling stars to influence their surroundings. Yet radiation alone does not guarantee widespread warmth. As electromagnetic waves move outward from their sources, their energy becomes spread across larger and larger regions. The vacuum permits radiation to travel, but it does not preserve its concentration. Another important factor is continual radiative cooling. Every object in the universe emits radiation. Planets radiate energy into space. Dust grains radiate energy. Gas clouds radiate energy. Even the warmest bodies lose energy through electromagnetic emission. Unless incoming energy balances or exceeds outgoing energy, cooling occurs. Warmth, therefore, requires maintenance. It is not a permanent condition. The cosmic microwave background provides a useful reference point. This faint radiation fills the observable universe and represents the cooled remnant of a much hotter early epoch. Today it corresponds to a temperature only a few degrees above absolute zero. In regions far removed from significant heat sources, objects tend toward thermal conditions influenced by this background environment. The existence of this universal glow demonstrates that space is not completely devoid of energy, yet it also highlights how cold the average cosmos has become. The structure of matter contributes as well. Stars occupy only a tiny fraction of cosmic volume. Galaxies themselves occupy only a small fraction of the observable universe. Most space exists between concentrated sources of energy. The brightness visible in astronomical images can sometimes create a misleading impression, because cameras often emphasize luminous regions. In reality, darkness and emptiness dominate the overall volume. Even within galaxies, cold conditions are common. Molecular clouds remain shielded from intense radiation. Interstellar space contains sparse matter spread across enormous distances. Outer planetary systems receive only weak stellar illumination. The pattern repeats at every scale. Localized regions of warmth exist, but they are surrounded by much larger regions where energy remains comparatively scarce. Earth illustrates the difference between a warm world and a cold universe. The planet receives a steady supply of solar energy. Oceans store heat. The atmosphere redistributes energy and slows its escape. Together, these processes create conditions suitable for liquid water and life. Yet Earth's warmth depends upon specific circumstances. Remove the atmosphere, remove the oceans, or greatly increase the distance from the sun, and temperatures would change dramatically. The broader lesson extends beyond Earth. Warm environments are often the exception rather than the rule. They arise where energy sources, material properties, and physical conditions align in particular ways. Coldness, by contrast, emerges naturally from the fundamental structure of the cosmos. Vast distances separate energy sources. Matter remains sparse. Radiation spreads outward and weakens. Objects continually emit energy into space. Observations gathered by NASA ESA/ESO and many scientific institutions reveal a universe governed by these principles across every observable scale. From planetary systems to galaxy clusters, the same underlying physics appears repeatedly. Energy flows through radiation. Distance reduces intensity. Sparse matter limits direct heat transfer. Cooling operates continuously. Together, these processes create a cosmos where warmth exists locally, but coldness dominates globally. Space is therefore not cold despite the sun's incredible heat. It is cold because the sun's heat, powerful though it is, must obey the laws governing energy and distance. The same principle applies to every star in every galaxy. Their light travels across the darkness, carrying energy through the vacuum. Yet the universe is simply too vast for that energy to remain concentrated everywhere. The hidden physics of the universe reveals a simple conclusion. The cosmos contains extraordinary sources of heat, but it contains far more space than heat sources. Radiation travels freely, yet it spreads. Matter exists, yet it is sparse. Energy is generated continuously, yet cooling never ceases. From these realities emerges the thermal character of the modern universe, a place illuminated by countless stars enriched by immense energies, and nevertheless defined across most of its volume by enduring cold. As the exploration reaches its quiet conclusion, the immense structure of the universe settles into a simpler perspective. Across the observable cosmos, stars continue to shine. Galaxies continue their slow motions through space. Radiation travels across distances measured in millions and billions of light years. Yet beneath this constant activity lies a remarkable balance shaped by the fundamental laws of nature. The sun appears powerful because it is nearby. Its warmth fills daily life on Earth and influences nearly every process at the planet's surface. Countless other stars perform similar roles within their own systems. Each creates a local region where energy gathers, where planets may warm, and where matter responds to incoming light. These pockets of warmth are real and significant. At the same time, the spaces separating these sources are far larger than the sources themselves. The universe is not primarily composed of stars. It is composed of the vast distances between them. Radiation crosses those distances, faithfully carrying energy through the vacuum, yet it becomes increasingly dispersed along the way. The farther it travels, the more thinly it spreads. Throughout space, objects quietly exchange energy with their surroundings. They absorb radiation, emit radiation, warm, cool, and gradually move toward balance. Dust grains drift through dark clouds. Icy worlds orbit distant stars. Galaxies shine across immense separations. Everywhere, the same physical principles operate with calm consistency. The coldness of the cosmos is therefore not an unusual condition requiring special explanation. It emerges naturally from scale distance and the manner in which energy travels. Warmth remains concentrated near its sources. Coldness fills the vast regions beyond. In that sense, the universe presents a quiet contrast. Brilliant stars illuminate the darkness, yet they do not erase it. Great energies are produced, yet they do not fill every corner of space. Light journeys endlessly through the vacuum, while the larger cosmic landscape remains calm, sparse, and cold. Across billions of years, this balance endures. Stars are born, stars evolve, and stars fade. Radiation continues its journey through the immense openness of space. The cosmos remains a place where heat and cold coexist, shaped not by mystery, but by the simple and elegant laws governing energy, matter, and distance.